Good afternoon. Hi, everyone. I am thrilled to be here. And I guess you can see what we're going to talk about today. We're going to talk about some of the things that Belmiro's team and my group have been working on in order to develop OpenStack for the kind of scientific research use cases that we both have in mind. So I guess for as long as OpenStack has actually been OpenStack, there have been people wanting to harness it for research computing. And there are many success stories across the community, and I guess that the CERN project is the most prominent, the flagship one of those. But now we want to look at, they've done that, we've got this far, and we want to look at the new ways we can take it further and get even better support for research computing environments. So how can we develop those use cases, and how can we develop OpenStack to be better suited for them? And that's what we're going to be talking about today. So that's me on the left. My name is Stig. I have been working for just over 4 years now on OpenStack. I started at Cray in the UK, and then we founded a company called Stack HPC, which is a specialist consultancy for developing OpenStack applications. We've been working with the SKA project on this performance prototype platform, which I'm going to be talking a little bit more about. And I'm also one of the co-founders of the OpenStack Scientific Special Interest Group. So here's Belmiro.
Hello, everyone. I'm Belmiro. I'm a cloud architect at CERN. I've been working with OpenStack for a long, long time now. So let's start. To describe the purpose of our project, let's start with the biggest graphic representation that I could imagine, so the universe. What you see there is 13.7 billion of years in one slide. From the start, the Big Bang, till today. So in the first moments after the Big Bang, the universe was extremely hot and dense, actually billions of degrees hotter than it is today, anywhere else in the universe. So this gave particles high energy and extreme properties that we don't have today. So these conditions don't exist anymore in the universe. So scientists at CERN, what they try to do is to recreate these conditions. To do that, we are at CERN. CERN is the European Organization for Nuclear Research. It's the biggest international collaboration in the world. For you to have an idea, 10,000 scientists from more than 100 countries work at CERN. And for the research, CERN operates a complex network of particle accelerators. A particle accelerator is basically a machine that propels a beam of subatomic particles to speeds very close to the speed of light. And this one that you see there, that the representation, is the LHC, the Large Hadron Collider, and is basically the biggest machine in the world. It's an accelerator with 27 kilometers. It crosses 2 countries, and all of this is 100 meters underground. You can see there the Geneva Lake, the Swiss Alps, the CERN headquarters. And we use this big accelerator to accelerate particles. Actually, the LHC accelerates 2 beams of particles, and they collide in those 4 points that you can see there, the CMS, LHCb, Atlas, and ALICE. And when they collide, these are basically mini Big Bangs that we get. This is inside the LHC tunnel. What we see there, they are magnets, these blue pipes. There are 10,000 of them. These are not ordinary magnets. They are superconducting magnets. And to achieve this state, they need to be operated at a very low temperature, minus 271 degrees Celsius. You can imagine only to cool down everything takes weeks and a lot of helium. These are huge magnets. They are between 5 to 15 meters. and some of them can weigh up to 35 tons, each one. So the particle beams are accelerator in the accelerator, and they collide. And there, we have detectors to see the collisions. This is one example of one of the detectors. And these machines are huge. They can have up to 45 meters long, 25 meters in diameter, and weigh more than 12,000 tons. As an example, this one, CMS, has more iron than the entire Eiffel Tower in Paris. And all of this, remember, is 100 meters underground. A detector is basically a digital camera, not ordinary digital camera. It takes 40 million pictures per second, and this can produce up to 1 petabyte of data, raw data, per second. Of course, we don't have capacity to store all of this. So we need to select the most interesting events live, basically. So with all this filtering, we reduce from 1 petabyte to a few gigabytes per second, and is what we store. So last year, 2016, CERN stored 50 petabytes of data, only last year. With all these collisions, then scientists can have a representation how particles interact, and to have insights, basically, how the universe works. So to process all this data and to support the research of scientists all around the world, we have 2 data centers. One is in Geneva, the other is in Budapest, Hungary. And we are running OpenStack in both of them. 2 data centers, however, we only have 1 region. And these are a few numbers about our clouds. We have around 280K cars, this in 8,500 cars. So I'd like to show you a brief overview about our architecture. So these big boxes represent the 2 data centers that we have. All the OpenStack control plane is in Geneva. Also, we have a Ceph instance, plus some DB on-demand servers. You can see that we have cells. We still use cells v1. Actually, we are one of the biggest cells users. And on Budapest, we only have cells, compute cells, basically, because all the control plane is in Geneva. Of course, we still need to have the DBs for each cell there, because the latency. And also, we have a Ceph instance for the same reason. So
that's pretty awesome. So if CERN is looking at that very first nanosecond, then the SKA is looking at the rest of time. And really what we're interested in looking at here is to take the, well, I guess that the LHC is looking to answer some of those fundamental questions to do with the Big Bang, and we're trying to work out what happened next. So the SKA, the Square Kilometre Array project, is a set of radio telescopes of unprecedented sensitivity. And it's being designed really to help us understand more about the mysteries of cosmology from that moment forward. So we've got a couple of the primary science cases of the SKA to talk about here. So this is what they call the Epoch of Recombination and the Epoch of Reionization. So this is the moments between about 400,000 years after the Big Bang to about 400 million years after the Big Bang. And in that time, before that time, the universe was just too hot and too energized for any light to propagate. So the universe was a black box in the truest sense. And then at the point of the Epoch of Recombination, it started to become transparent. So now we can start to see the earliest things that are visible at this point. Seeing that far back through to the epoch of reionization and recombination, we get to see the early stars and the galaxies that form around about 400 million years after the Big Bang. And they are galaxies and stars that are not like the galaxies and stars that followed after. So they're unique, they're strange beasts, they're very large, they're very different. And so it It gives scientists a unique insight to be able to see these things more clearly. Another use case that the SKA has is to look at pulsars. Firstly, to detect them across the universe and to map them out, and also to find the ones that are really, really spinning fast, so spinning thousands of times a second. And the purpose of finding these is a project to sense gravity waves. The Nobel Prize this year went to the team behind LIGO for hearing the first gravity waves. And this is an entirely new way that people can sense the universe around them. It's an entirely new way that has no bearing on light or electromagnetism or any of those things. Totally different, and that's pretty special. So LIGO is able to see the biggest, loudest, brightest events in gravity wave emissions. They can see the collisions of black holes, which you might think is a pretty rare thing, but it turns out that they've seen 3 in the last couple of years. So the universe does some strange stuff more often than we think. To do this, they built some 4-kilometer-long tubes, and they could detect, with that 4 kilometers of sensitivity, they could detect gravity wave effects to about the 1,000th the size of an atomic nucleus, which is about the limits of anything that the sensitivity of their detectors. So the SKA plans to make a far bigger device by harnessing pulsars across the galaxy and across the universe in order to create far longer axes and then sense the motions and the ripples of gravity waves as they pass by. One of the other interesting projects and challenges that is raised by this is that things like black holes colliding, events like that in the universe tend to happen more often than we think. And we really want to be able to catch these rapidly changing events, this real flux. So things go pop on a regular basis, on a frequent basis. And one of the challenging, or the most challenging aspects of the SKA's science is to sense and alert when these things start to happen. So that brings in, as well as this kind of immense data processing challenge, that brings about the issue of how do we create an event detection in real time or near real time, and then refocus the telescope's observations onto what's just happened. The machines are actually across 2 major sites. They're in the deserts of Australia and South Africa. And the project currently is moving through prototyping phases. So these machines here are the Australian SKA Pathfinder. They have 36 of these dishes. And that is one of the physical prototypes that has been deployed as part of the SKA's early phase prototype program. Production science workloads are not expected until about 2023, which gives us a little bit of time to develop the kind of infrastructure which can consume the data rates that these devices are going to be generating. So to do that, the compute is extremely demanding. To process the data that's coming from these antennae, they estimate they're going to need about 250 petaflops of compute power. So the biggest machine in the world today is about 70 petaflops. So this is a massive, massive undertaking. If you think about it, the efficiency of this machine is critical. 1% efficiency loss is equivalent to something like the 60th most powerful computer in the world today. You can't just throw that away. So this machine has to be highly tuned and yet also highly flexible and adaptable. The project really tends to take advantage of software-defined infrastructure to the fullest extent that it can without sacrificing anything on performance. So at the heart of the machine is what they call the Science Data Processor, or the SDP. This is the supercomputer. There is going to be one of these in Western Australia, and there's going to be one of these in South Africa. Each of them consumes about 1 terabyte a second of raw data from the signal processors and correlators going close to the telescoped antennae in the desert. The data that these machines must consume, they have to hold it for 6 hours. And then they have to hold the processed data for about 6 months. and that's about the limits of affordability in order to do the primary science objectives. The algorithms that are used in order to process the observations and generate meaningful image data from them, they're not completely parallel. So there is enough locality enable us to design an architecture based around islands of compute. The islands are themselves tightly coupled, but the connectivity between the islands can be a little bit oversubscribed, which makes the whole thing possible and affordable. So the SKA is a massive project, and this is my small corner of it. With Cambridge University, we've been working to develop a system called Alaska, which is a performance prototype platform. The purpose of this machine is to inform the decisions on the architecture of the production system. So what we have to create is a level playing field for the scientists who are working on defining the SKA compute pipeline to enable them to make informed decisions about the way to proceed. The scientists want to explore all the different possible options, a great breadth of diversity, and this machine needs to be able to deliver a representative comparison between these different strategies. Using OpenStack, we have been creating a dynamic platform for performance prototyping, and the vision we've got is really, it's a polymorphic computing, but it's also got to be high performance. It can't have any overhead. So it's all bare metal, and yet it's also highly reconfigurable. So the way that we look at this is that if we have different workloads and they have different requirements of the system, we need to be able to reconfigure the BIOSes, the storage, the kernel parameters, these other things, in order to optimize it as best we can to one particular workload or another. So going back to the previous graph, previous diagram, we have a model of 2 islands. Essentially, it's 2 racks. But we also have a wide range of different kinds of hardware in this system. We've got a few GPU nodes, a few high memory nodes, a few nodes that are stuffed with NVMe devices. We've got an ARM64 Ceph cluster from Softiron for the clusters level application storage. This is a bare metal OpenStack system. It's using a containerized Collar control plane, and everything in it has been deployed from repos using Ansible and Bifrost. Already, what this machine is doing is pushing the boundaries of many of those components and has already generated a good deal of upstream activity based on the experiments that have gone on so far, both in the control plane and in the applications above. Now, these 2 people are the Director Generals of CERN and the SKA project. And they recently, over the summer, they signed an agreement for a technical collaboration developing the next generation of research computing infrastructure. The alignment is pretty clear in terms of the demands of the 2 projects. Our OpenStack team met with Balmero's OpenStack team, and when we compared the challenges, we found a lot of common cause. So we came up with a list of problems and agreed to try to work together on creating common solutions to those. And that's a little bit about what we're going to talk about now. So SKA is not going to go into production until early 2020s, which is probably just enough time for the OpenStack Z release to come out. So we've got a little bit of wriggle room to develop these components. That doesn't mean we shouldn't start right now. So, Balmero.
Also for CERN, in 2023, the LHC will be upgraded to the high luminosity LHC. This means that we're going to increase the performance of the actual accelerator that we have 10 times. And all of this should be ready by 2025. So we have this little interval to figure out how to do this in terms of computing. What we expect, considering the current hardware, software, and analysis technology, is that we're going to need more than 50 times more computing power that we have today after the upgrade of the LHC. In terms of data storage, we predict that we will enter in the exabyte scale by that time. Because of these similar challenges between CERN and SKA, we are now working together in this collaboration. And of course, we invite all of you to join us So there are several areas of interest between these two projects. We're going to focus in this presentation in only a few of them. We're going to start with the bare metal hardware lifecycle. That is a common problem, I think, for everyone. The difference could be the scale. So in terms of CERN, we buy around 2,000 servers per year. Considering the amounts involved, a formal procurement process is needed. In our case, each procurement process takes around 200 days. And given all this time that it takes, of course, we cannot go using a module, a continuous delivery model. We need actually to do annual planning. So we know after the annual planning that that project will need these resources. And these resources, when we receive hardware, are actually allocated to that project. We have limited capacity in our data centers. This limitation comes usually by power constraints. One of our data centers has 3.5 megawatts, the other 2.7. So when new hardware arrives, we need usually to retire old hardware. We typically retire hardware between 4 to 5 years old when the CPU power watt ratio is not worth enough to keep the hardware running. And one of the challenges is really retiring hardware. Batch workloads are easy. We just train the nodes. For you to know, in terms of batch workloads, around 85% of our cores are dedicated to batch, but this only represents 2/3 of the entire VMs that are running in our cloud. Around 10% then of the CPUs are dedicated to service VMs, running IT services, for example. And those represents 1/3 of all the VMs in our cloud. And those are quite challenged to migrate then to the new hardware. So in each procurement, we have 2 to 3 vendors involved. We have some advantages with this. Like if there is any problem with the vendor, the procurement process is not all affected, only a few parts of it. For example, if there are issues with disk firmware, BMC controllers, whatever. The disadvantage is that we have a lot of different configurations in our data center. And our tooling needs to support all these different configurations, of course. Also, another challenge is the flavors that we expose to our users. They depend on the different hardware configurations that we have. So we started to look into Ironic a few months ago. So the main motivation is because we like to have OpenStack as a single pane of glass to allow our users to deploy VMs, containers, and also bare metal. So using only OpenStack APIs. This is great because we can use the same traceability and accounting that we use for VMs to physical nodes. But we start thinking, and since we are implementing Ironic, we start thinking, can we use Ironic to manage all the hardware lifecycle? Because until now, we are building over the years our own tooling. Since the new server enters our data centers until it's retired. So what are the requirements, at least for us, to manage the hardware lifecycle? Well, we need a database, basically, to store all the hardware attributes. So this means the manufacturer, product revisions, all the firmware revisions that go through a specific hardware. A flexible and complete hardware introspection. We would like to collect as much information of the hardware that arrives as possible. A flexible API then to query this information in an easy way. A burn-in and acceptance process, so something that actually test the hardware before it's accepted and delivered to the users. Of course, for this, we need a staked workflow and a clear retirement procedure. So for you to have an idea, this is our current workflow at CERN for the hardware. I will not go through this. This is for you only to have an idea how complex could it be. It's complex, but it's automated using the tools that we've been developing. However, what we would like, what we envision with Ironic is to do exactly the same, but using a tool that everyone else can use. So for this, what we expect is, again, maybe it will continue to be complicated, but automated, and generic. Pluggable, because not everyone has the same requirements for burn-in, for example, and acceptance of the hardware, and track the resources.
Our scale is obviously about 1,000th of the scale at CERN because we are just prototyping. But that gives us a good deal of freedom to explore and to experiment ourselves. And at this comparatively tiny scale, we can play a bit. And so what we've been doing on our project in the performance prototype platform has been to really take as much as we can from advanced Ironic functionality and make the most of it in order to model the process of auto-discovery and auto-enrollment at scale. So a lot of what we've been doing has been to bring Ansible in to orchestrate and configure every stage of our hardware lifecycle. And we've been successful in doing this from everything from the BIOS parameters and the RAID parameters, the network switch configurations, and everything about the deployment process of the compute nodes, from there on up to the deployment of OpenStack itself. So we use Collar Ansible to do that. And the whole process from the very first discovery and registration of the compute nodes up to the point where OpenStack is running and we've configured it with provider networks and flavors and images that we're using as the sort of reference state of our platform. That's all controlled and contained in one repo. So there's infrastructure. The entire infrastructure is in one consistent layout, in one document, in one YAML repo. So that's pretty cool. The end result is that we have a nice redeployable infrastructure. Not that we redeploy it very often because we do have users, but this is an area where my team's background, working with the SKA project and the research that we've been doing, has created something we feel is pretty special and is something that we'd love to share back. Somewhere where we really look to CERN for leadership and experience is in the application storage. So CERN's storage problems are obviously huge and complex. And this is an area where the SKA project is hoping to benefit from their hindsight. And no doubt, quite a few painful lessons as well. So we have massive impending challenges of our own in storing, retrieving, and distributing data sets. In today's technology, we can just about consume the data rates from one of the telescopes with many hundreds of the highest spec NVMe devices. With about 10,000 of these high-spec NVMe devices, we can meet the challenge of storing about 6 hours of this data. An important distinction for us is how the storage is managed and owned. So we're looking at these abstraction layers and whether the storage is managed by the infrastructure or whether it's created and managed in a sort of a hyper-converged manner inside the bare metal platform itself. So this is an area where we're doing quite a bit of research at the moment. And so we must store a very high data rate from the dishes. We've got to hold it for about 6 hours. We've got to store the processed data and hold it for about 6 months. And then we've got to create a way of sharing that data around the world to the SKA partner countries and to the scientists whose primary science objectives are being met by that data. That's a very different kind of challenge. The challenge of data federation is something that I don't think we have a clear handle on how to pursue that yet. And it's something that we'll be looking at in the next few years. And I think it's a very similar problem to the kind of challenges faced by the CERN team. So the solutions that we have at the moment, we're using a lot of heat and a lot of Ansible to create storage cluster services. And then we're bringing in different file systems, different object storage, different message queues, these different technologies. And we're trying to create these environments where we offer these as services to the scientific workloads themselves. We try and integrate them in a nice modular way, making the best use of each of them so that the scientists can get an objective comparison about the relative performance of those different technologies. And the way that they're using those is to consume them into application stacks that sometimes are domain-specific to radio astronomy, and sometimes are more general things like big data analytics stacks, that kind of thing. Our goal is to create an infrastructure that is performant, but is actually also very flexible so that we can run Kubernetes or Docker Swarm one day, and we can run MPI and Slurm and scientific applications another day. We want all the flexibility of cloud, but we don't want any of the performance overhead that's perceived to come with it. We want to give the scientists who are our users the infrastructure and let them get on with what they want to do without obstructing their progress. So how do we provide these complex applications optimized for these systems? And how do we do that as a service? And then how do we share that between the contending users?
So one of the areas that we are very interested is how can we have clouds that are more efficient, actually use all the resources that are available. And that is the goal of printable instances. So basically, scientific clouds have different founding models. However, in most of the cases, they are predefined resources for a project. So the project will know that we'll have X number of cores from the beginning. Having resources available and allocated doesn't mean that the scientific project will actually use them. So in most of the cases, they use the resources from some time, and then they are free. And they actually can be used by other projects. So public clouds solve this kind of problem with a spot market. When they have available resources, resources are cheaper. They increase the price and actually kill the VMs when they need the resources. In OpenStack, we don't have anything to do this. Actually, we also don't charge the final user. So what we start looking at is how can we have preemptible instances into Nova? So the approach that we start looking at is basically start identifying instances with a tag saying this instance will be printable. So the SLA is very low, could be killed if actually a project needs to fill up its quota. So when the Nova scheduler detects that there is no more space available, what we will do, it will send a no-valid host, like today. And then we can have, or we are prototyping a Reaper that will get that no-valid host, and we will kill the printable VMs that are in the clouds to make space available for the project VM. We just start prototyping this. We are actually asking for our help on this. So we have an header pod where all of this is described. We actually have the code of the prototype in our GitLab. So please have a look and participate on this. We also start looking into Magnum and bare metal. Performance is important for scientific clouds. Actually, CERN was one of the first sites using Magnum into production. We currently have several users with different use cases. Jupyter, notebooks, batch processing, Currently, we offer with the 3 COEs, Kubernetes, Docker Swarm, DCOS, and but all of this is still in VMs. And with collaboration with SKA, we start looking, how can we have this on bare metal?
So yes, we took the Magnum project and we worked through several issues in getting it running on latest OpenStack Pike and a Kata before that with the bare metal drivers. And we've been contributing those pieces upstream and talking through the experiences with the CERN team, who are specialists in Magnum. And in return, we've also been having a discussion about how the CERN team have been mapping their Ceph storage into their Magnum clusters. And so this kind of collaboration has been very useful for, I think, for both parties. We've also been looking at how do we do high-performance Spark and Hadoop. So one of the interesting pieces here is a project which I'll just quickly touch on, which is this one for big data over InfiniBand and other RDMA-enabled transports. This gives us a huge uplift in terms of the overall throughput and much lower utilization of processor when we're using a communication-intensive Spark or Hadoop deployment. And we have been working on deploying Sahara drivers, which will integrate HighBD, the RDMA-enabled big data stack, and we've been working to get those ironed out and get the pieces of work upstream where we can. And finally, we've been doing a piece of work with projects like OpenHPC, and we've been developing heat stacks which will deploy clusters for more conventional kind of HPC InfiniBand-driven compute using conventional HPC libraries like MPI, but also mapping in things like our user directories in CephFS, using Barbican to manage the project keys for these pieces, and bringing together essentially Slurm as a service driven by Heat, configured by Ansible, and supported by Ceph and Barbican. You might think that this is all very well, but actually, I just want to emphasize that this is actually all completely open, and everything that has been done so far in this collaboration is upstream. In terms of the source code, everything's gone back up to OpenStack repos. And in terms of the knowledge and the information, a lot of it is being shared through the OpenStack Scientific Special Interest Group. So if you haven't heard of that and you're interested in understanding how OpenStack can be adapted to scientific use cases, I do encourage you to take a look at the microsite that the OpenStack organization has set up. I also have a few of the books. This is the book on the right, which the working group has generated over the last year or two. It's now in its 2nd edition, and I have a few of those if anyone's interested afterwards. Come and grab one. So OpenStack develops fast, but we've got a little way to go. And what do we need to do if we were to bring OpenStack into production in 2022 on machines like the new high luminosity at CERN and the SKA deployments? We're not really sure yet. So there's a lot of collaboration and a lot of investigation that needs to be done. By the time these machines enter their production phases, OpenStack will be on its Z release. And after the SKA's 50-year operational cycle is complete, it will have gone 3 laps round the alphabet of OpenStack releases. That's a lot of development time, and that's a lot of opportunity to collaborate and work together. We hope that it will develop to support processing workloads like these machines and the detectors at CERN, but it's not going to happen unless we all do it together. So, thank you very much. Do you have any questions? No? Oh.
Do you have a question about it?
Thank you.
All right, thank you.